Have you ever stopped to think about how your electronics make such clean, decisive choices in what's actually a pretty messy and noisy world? Well, it turns out there's this brilliantly simple trick that circuits use to just ignore all that interference and make smart decisions. And today, we're going to break it all down. Okay, let's start with a really simple question. Think about your thermostat. If you set it to, say, 70 degrees, why doesn't it just go completely crazy, clicking the heat on and off, every single time the temperature wiggles from 69.9 to 70.1? The answer is a super clever bit of electronic engineering, and that's what we're about to unpack. You see, at the very heart of this are electronic decisions. Circuits are constantly having to answer these simple yes or no questions. Is it too hot? Is the button being pressed? Is the tank full? And to do that, they rely on a really fundamental component. And that component is the comparator. Its job is incredibly simple, but it's also crucial. It just looks at two different voltages, and if one is higher than the other, its output snaps to high. If it's lower, it snaps to low. That's it. There's no in-between, no maybe. It is a decisive all-or-nothing kind of switch. A really great way to picture this is to think of a seesaw. You've got the two voltages on either end. The second one side gets even a tiny bit heavier or has a higher voltage, that seesaw doesn't just lean a little. No, it slams all the way down. The simple mechanism is really powerful, but it has one critical weakness. And that weakness, well, that brings us to the villain of our story, electrical noise. You know, in the perfect world of a textbook diagram, electrical signals are these beautiful, clean lines. But in the real world, things are a whole lot messier. Every single electronic signal in the real world has these tiny, random fluctuations just riding on top of it. You can think of them like little ripples on the surface of otherwise calm water. This noise comes from all sorts of interference, and it can absolutely wreak havoc on a sensitive decision-making component like our comparator. So you can probably see where this is going, right? What happens when our wobbly, noisy signal is hovering right around the comparator's trigger voltage? Well, the signal is constantly crossing and recrossing that line, not because of any real change, but just because of all those random little wiggles. It's like this. Imagine a light switch that is so ridiculously sensitive that the slightest vibration in the room, someone walking by, a truck driving down the street, causes it to just flicker on and off uncontrollably. That is exactly what happens to a simple comparator, and this crazy effect actually has a name. It's called chattering. And this chattering isn't just some minor annoyance, believe me. It causes the output to flip back and forth wildly, which wastes a ton of power. It puts a lot of physical wear and tear on components like motors and relays. And ultimately, it just makes the entire system completely, totally unreliable. Okay, so how in the world do we fix this? How do we build a smarter switch that isn't so twitchy? Well, the solution is actually incredibly elegant. We just give the circuit a little bit of memory of what it just did. And this whole concept is called hysteresis. It's a fancy word, but it basically just means that the system's behavior depends on its past. For our circuit, it means that once the switch is flipped on, the rule for flipping it back off actually changes. The circuit literally remembers what state it's in. Let's go right back to our thermostat example, because this is exactly how it works. It doesn't use a single trigger point. No, it has two. It might turn the heat on when the room drops to, say, 19 degrees Celsius. But once that heater is on, it's not going to turn off until the room warms all the way up to 21 degrees. That 2-degree gap in the middle, that makes it totally immune to all those tiny little temperature wiggles. So yeah, this two-threshold trick, that's the core of the solution. It's a fundamental technique that lets you build a much, much more robust and reliable system. Okay, here it is. This is the big aha moment. A simple comparator has one tripwire, just one. A hysteresis comparator, on the other hand, has two, an upper one and a lower one. And the space between them creates this safe zone, this deadband, where noise is completely ignored, all because the circuit remembers if it was last turned on or off. So here's how it actually plays out. First, the incoming signal has to rise all the way past that high threshold to turn the switch on. Got it? But the very instant that happens, the circuit instantly changes the rules of the game. It moves the threshold way, way down to a new lower level. And now the signal has to fall all the way below that new point before the switch will even consider turning off. And that gap, that space between the turn-on point and the turn-off point, that's what we call the hysteresis window, or sometimes the deadband. Any noise or little fluctuation that stays inside this window is totally powerless. It can't affect the output at all. The switch is just rock solid and stable. So to make this a little more concrete, just imagine a sensor that's monitoring the liquid in a tank, where splashing around creates a ton of noise. If the desired trigger point is, say, 1 volt, engineers might design a deadband of about 150 millivolts. And that ensures that even if the liquid sloshes around, causing all these little voltage changes, the output stays stable unless there's a real significant change in the liquid level. And this isn't just some niche, nerdy electronic trick. I promise you, once you know what to look for, you will start seeing hysteresis everywhere. It is a fundamental principle for making robust systems that can survive in the real world. In fact, the idea goes all the way back to 1934. There was an inventor named Otto Schmidt, and he was trying to solve this exact problem of chatter in these really noisy early telegraph signals. His solution, which he called the Schmidt trigger, was so effective that it became a fundamental building block that's still used in countless devices today. You see this principle in action all around you. Your thermostat, of course. The push buttons on your phone or your remote control use it to ignore the tiny physical bounces that happen when you press them. And really critical systems, like the sensors that measure your car's wheel speed for the anti-lock brakes, rely on it to get a clean, reliable signal, which is pretty important. So, really, when you boil it all down, hysteresis is just the simple act of adding a little bit of memory to a circuit. And by remembering what it just did, the circuit becomes smarter, way more stable, and totally immune to the chaos of real-world noise. It's an incredibly powerful concept, and it really goes way beyond just electronics. It kind of makes you wonder, right? What other problems, maybe in our daily lives or even in more complex systems, could be made more stable and more robust just by adding a little bit of memory, a little bit of history?